Hello, friends. This is Josh Price. I'm coming to you from my desk at home. Happy snow day. Hope you're staying safe. Today, we're going to continue our discussion of the SN2 and E2 reactions. We're going to talk about what factors favor either of them, and we'll also talk about their stepwise counterparts, the SN1 and the E1 reactions. We'll try to put it all in context. So last time we were talking about competition between the SN2 reaction, which is concerted by molecular substitution, and the E2 elimination reaction, which is concerted by molecular elimination. And the reason for this competition is that we learned, because of hyperconjugation, the LUMO of an alkyl halide is both on the alpha carbon, that's the carbon connected to the halide leaving group, and on the beta proton. We discussed that last time, so check your notes for details about sigma to sigma star hyperconjugation. For the SN2 reaction, we said the rate is dependent on the concentration of your nucleophile/base and on the concentration of your alkyl halide. We form the new nucleophile carbon bond at the same time as we break the carbon leaving group bond. Substitution happens when the nucleophile attacks the LUMO, shown here as being mostly the carbon bromide sigma star, but spreading out also onto the adjacent beta protons. When the nucleophile attacks the alpha carbon, dumping electrons into the sigma star, and then the leaving group leaves. Backside attack is how this happens, and we get inversion of stereochemical configuration. I've tried to show that here, where the oxygen in the nucleophile ends up sort of opposite to where the bromide was. Here's an alternative view. The CBr bond was coming up, and then the nucleophile comes in, and the new carbon-oxygen bond is pointing down into the page. The key mechanistic stereochemical issue here is that we have backside attack, because that's where the sigma star is. And so if our leaving group is at a stereocenter when the nucleophile attacks, and the leaving group leaves, the nucleophile has to come in from the opposite side. Whereas the leaving group was up, now the nucleophile attached to the carbon is down. In terms of the E2 reaction, elimination occurs when, instead of attacking the alpha carbon, the nucleophile attacks at one of the beta protons. Now remember that in order for the LUMO to spread out onto the beta proton, the carbon-hydrogen bond must line up with the carbon halide sigma star. And the only way for that to happen is for the carbon-hydrogen bond to be anti to the leaving group on the adjacent atom. If we were to do a Newman projection and look down this bond between beta carbon 1 and alpha carbon, we would see that hydrogen A here, blue hydrogen A, is anti to the bromide leaving group. And notice that the LUMO is only on those protons that can be anti to the leaving group. The LUMO is not on protons C and B here, because they are not currently aligned with the leaving group. Of course, we're allowed to rotate around carbon-carbon bonds, and we'll see that in just a second influence the kind of products we can get. So if our nucleophile attacks proton A on beta carbon 1, we get the following product. We remove beta proton 1, electrons from that carbon-hydrogen bond kick down to form a new pi bond between alpha and beta 1. Then the leaving group leaves, all in the same step, and we form this alkene or olefin product. Both of those terms are interchangeable. Olefin is a term for derived from the petroleum industry for molecules with double bonds. I'll use alkene and olefin interchangeably. So the new pi bonds between alpha and beta carbons, beta carbon 2 remains unchanged. And I'm not showing three different products. We have three protons on beta carbon 1. Any of them, by rotation around this carbon-carbon bond, could be anti to the leaving group. Of course, because all of these protons are identical by symmetry, it doesn't matter which one gets removed, and there are no stereoisomers possible here because on the beta carbon 1, we just have two protons. There are no cis or trans issues to deal with. However, we do have another beta carbon here, beta carbon 2. And on beta carbon 2, we have a methyl group, proton A and proton B. Now, if beta proton A is the one that is anti to the leaving group, a base can remove beta proton A. These electrons would kick down, form a new pi bond, the leaving group would leave. We would form the new pi bond between beta 2 and alpha. And if you look at the molecule as we've drawn it here, the methyl group on beta carbon 2 is coming out toward us, as is also the methyl group on the alpha carbon. Both methyl groups are coming out toward us, so both of them are going to be on the same side of the new pi bond that we make. So if we remove beta proton A, we have to get the cis isomer. Because we will see that beta proton A, purple beta 2 proton A, and purple beta 2 proton B are not identical because they lead to different products. For example, if we start with the same structure shape that we have up here, and we rotate around the bond between purple beta 2 and alpha, such that beta proton B swings down to become anti to the leaving group. If we do that, methyl group would be pushed back into the page, and proton A would swing up, and we would end up with this structure. Now proton B is anti to the leaving group, and if we remove proton B and make the new pi bond between alpha and beta 2, notice that in this conformation of the molecule, methyl group on beta 2 is pointing back into the page, whereas methyl group on alpha carbon is pointing out in front of the page. They're on opposite sides, and therefore they must be trans to each other in the product that we form. Again, we attack at beta proton HB, purple HB, that gives us a different diastereomer than if we attack at beta A. So a full consideration of both SN2 and E2 reactions would give you this substitution product, and you would have to get the right stereoisomer. That is, you'd have to show inversion of configuration, and you would need to show all three of these elimination products. This, what we're going to call, because there's only one non-hydrogen group on the alkene, we'll call this a mono-substituted olefin. Substituted here doesn't have anything to do with substitution reactions. An unsubstituted olefin would be like C2H4, like this, where none of the groups attached to the carbons of the alkene are anything other than hydrogen. If we replace one of those with a non-hydrogen thing, that's a mono-substituted olefin, and so on. So we get one mono-substituted product, and we get two di-substituted products. We get this Z or cis isomer. We also get this E or trans diastereomer. And we will talk in just a little bit about whether you can expect one of these elimination products to dominate over the others. We mentioned last time that substitution reactions are favored by good nucleophiles, and that good nucleophiles are generally molecules with conjugate acids whose pKa's are greater than 0. So this would not include water or alcohols, but it would include things like carboxylates, thiolates, amines, alkoxides, and so on. In contrast, E2 is favored by things that are strong bases, and these are generally molecules whose conjugate acids have pKa's greater than or equal to 16. So you're thinking about alkoxides and hydroxide, deprotonated alkynes, and so on. And notice that there's going to be some overlap between these two categories, because anything that's a strong base will have a pKa. His conjugate acid will have anything that is a strong base will have a conjugate acid whose pKa is greater than 16, will also be greater than 0. We do have a category of nucleophiles / bases that are strong bases but are poor nucleophiles because of sterics. We'll talk about that a little bit later. But if you have a molecule that is exclusively a good nucleophile and not a good base, then you're going to be thinking about SN2 rather than E2. Now, we need to talk about how the structure of the alkyl halide influences the SN2 reaction. So far, we've just dealt with the nucleophile, but the alkyl halide shows up in the rate law too. So with the SN2 reaction, because of backside attack, the major issue the major issue is steric hindrance. So we will see that the rate of the SN2 reaction for methyl halides is very fast. For primary alkyl halides is also very fast. For secondary alkyl halides, not as fast, slower. And for tertiary alkyl halides, too slow to observe. In other words, we don't see any SN2 products for tertiary alkyl halides. And the reason for this is, again, steric hindrance. So let me just take you to the Spartan app, and we'll look at the difference between a primary or a methyl alkyl halide and primary, secondary, and tertiary. So we'll look at the space filling model. We'll also look at the sigma star. Notice that the sigma star, the LUMO is the carbon halide sigma star. A nucleophile would be attacking on the blue lobe that's on that carbon. And if we look at a space filling model, because there are no non-hydrogen things on the reactive carbon, it should be easy for a nucleophile to attack. And indeed it is. And the nucleophile can get in quite close to that carbon and make a new bond. Now, as we add another group, you can see that it will get a little bit more challenging. The LUMO is still the carbon hydrogen sigma star. A little bit of it's on that beta proton for reasons that we talked about. But if you look at the space filling model, we can still pretty much access that carbon that's bonded to the bromide leaving group. As we start to add another alkyl group to get to the secondary alkyl halide, we're going to see again in the space filling model that the LUMO gets a little bit less accessible. So let's look at that space filling model. The carbon in the middle there that's bonded to the leaving group is even less accessible to a nucleophile. Those other methyl groups get in the way. And finally, we will see that by the time we get to the tertiary alkyl halide, this molecule is not in our database apparently. So by the time we can't see the LUMO, it would be the carbon bromide sigma star. If we look at the space filling model, you can see that it's the little triangle there represents the amount of the alpha carbon, the one that's bonded to the leaving group, the amount of that alpha carbon that's accessible. And you can see it's not very much at all. And so the rate of SN2 is imperceptibly slow for tertiary alkyl halides. And again, the major issue is just sterics. The more non-hydrogen things we have attached to the alpha carbon, the harder it's going to be for the nucleophile to sneak past those non-hydrogen things to get to the alpha carbon. Interestingly, we observe that the rate of the E2 reaction follows kind of an opposite trend. For methyl halides, funny joke, there are no beta protons, so no E2 reaction. For primary alkyl halides, the rate of E2 is very slow. It picks up for secondary alkyl halides, gets a little bit faster, and is quite fast for tertiary alkyl halides. And what is the major issue here? Well, there are two sorts of things that we need to talk about. The first is if you look at a primary alkyl halide, excuse me, versus a secondary alkyl halide versus a tertiary alkyl halide, there are more beta protons on tertiary alkyl halides. So from a simple statistics point of view, it is easier to do an elimination reaction on a tertiary alkyl halide simply because there are there are more beta protons available. Each of these is a beta proton that's aligned with the leaving group, right? And each of them would be accessible for an E2 reaction. So so you've got a statistical issue that tertiary alkyl halides simply have more beta protons. The second issue is alkene or olefin stability. As we increase the number of alkyl groups on our alkyl halide, the elimination products tend to be more substituted, that is, more alkyl groups attached to the pi, to the carbons involved in the pi bond, and we will see that the more substituted an alkene is, the more non-hydrogen things we have attached to the carbons in the pi bond, the more stable the alkene is. We'll talk about why that is. There's an explanation for it. We don't necessarily need to talk about it right now, other than to say that more substituted olefins are more stable. And tertiary alkyl halides generally lead to more substituted olefin elimination products. Now, why should product stability affect the rate of the reaction? That connection is not totally clear yet, and we can talk about times when that product stability should influence the rate of the reaction. we will just say that for the E2 transition state, there is significant pi bond character. And therefore, transition states that lead to more substituted olefins will themselves be lower in energy and more stable. Okay? So, for example, for the reaction we've looked at here, we would predict that the monosubstituted olefin would form more slowly than the two disubstituted olefins. So we would expect the monosubstituted olefin to be the minor product and the two disubstituted olefins to be the major product. Because of sterics, we would expect the cis olefin to be less stable than the trans olefin because the methyl groups are not bumping into each other. And so we might expect the trans olefin to be the major product. Again, because the E2 transition state involves significant pi bond character, aspects, structural details that make a pi bond more stable will also make the E2 transition state more stable. We can illustrate that with a transition state diagram. Here I'm going to show you, let's see, alpha carbon, beta proton that's being removed, leaving group that's leaving, and a bond being formed between your nucleophile/base. There would be partial negative on the nucleophile, partial negative on the leaving group, and substantial pi bond character in the transition state. So again, what makes the alkene more stable will also make the E2 transition state lower in energy. So the more substituted alkene product will form more quickly. All right. So now we've talked about the SN2 and the E2 reactions and their stereochemical consequences. Let's do just a little bit of practice. Let's use the following alkyl halide and this nucleophile. Okay. To predict what's going to happen in this reaction, we need to consider the structure of the alkyl halide and the nucleophile. This is a primary alkyl halide, and we know that the SN2 reaction is fast for the primary alkyl halide, whereas the E2 reaction is slow. Second, if we look at our nucleophile/base, CN- is the conjugate base of HCN, whose pKa is around 9. Therefore, this is a molecule that is a good nucleophile, but a weak base. Good nucleophiles favor SN2. Weak bases do not favor E2. So we can predict that based on these two factors, the nucleophile favors SN2 and the alkyl halide favors SN2, we can predict that we would observe a substitution product. Okay? Similarly, if we used this secondary alkyl halide starting material, we would say, well, SN2 is possible for the secondary alkyl halide, and E2 is also possible. The rates of both of those reactions are sort of intermediate. for the secondary alkyl halide based on what we discussed above. A little bit faster for a secondary alkyl halide than a primary alkyl halide. For the SN2, it's not as fast for the secondary alkyl halide as for the primary alkyl halide, but we'll be worried about both possibilities. So now let's think about, now let's use, let's see, a different nucleophile. Let's use the azide nucleophile. Azide and N3 minus is the conjugate base of HN3, which also has a pKa of around 9. Again, this is a molecule that is a good nucleophile, but a weak base. So we're going to say that SN2 is fine, but because it's a weak base, we're not going to do E2. And therefore, we should see attack of azide anion on the alpha carbon from the backside to give a substitution product that would look like this. Notice that we have two stereocenters in this molecule. We don't change this one where the methyl group is. That one isn't involved in the reaction. Instead, we just have the nucleophile attack, chloride leaves, and we only see the SN2 product. All right. What if we took the same starting material, rather the same alkyl halide, but then let's use something that could be both a good nucleophile and a good base. So let's use CH3O- methoxide. Its conjugate acid is methanol, pKa 16. So this would be on our list of things that are both good nucleophiles and good or strong bases. So we would expect both SN2 and E2 to be okay. So in this case, with a secondary alkyl halide and a good nucleophile that's also a good base, we need to think of both SN2 and E2 products. To show the SN2 product, again, we're going to do backside attack of the nucleophile on the alpha carbon in the similar way as we did above. To indicate that we know that this reaction is an SN2 reaction, we must show inversion of stereochemical configuration. Now, for the elimination products, we need to look for the different kinds, look for any any beta protons that can line up with and be anti to the leaving group. So we'll call this beta proton 1, HA, beta carbon 1 with HA and HB. And then we'll call this beta carbon 2 with HA and HB. All right. So let me just ask, which of the 4 beta protons that I've identified, which of them can be anti to the leaving group? Remember, in a ring, you don't have completely free rotation around carbon-carbon bonds. That is, proton A, purple proton A, is always going to be trans to Cl, whereas purple proton B is always going to be cis to Cl. So which protons on either of the beta carbons can be anti to the leaving group? For the purple beta carbon, only beta proton A can be anti to the leaving group. For the blue beta carbon 2, only A can be anti to the leaving group. So we can show two potential products. One we would get by removing purple proton A, kicking electrons down to form a pi bond, and leaving group leaves. So I will draw that E2 product in purple. And notice that purple proton B is left behind, whereas purple proton A is removed. On the other hand, if I instead have my methoxide act as a base to remove blue beta proton, then the product I'm going to get, I'm going to show over here in blue, is going to look like this. Left behind will be blue beta proton, and we'll have this product. Okay. So we would expect to see these three products. If I were to ask which of the elimination products would be the major one, it would be difficult to say because they're both di-substituted, so I wouldn't expect you to identify which was major versus minor. I also will not ask you whether the substitution or elimination products dominate here. You would simply have to do the experiment, expect to find all three, and then see what happens empirically. All right. Let's deal with primary alkyl halide and a molecule that is both a good nucleophile and a good base. And actually, I'm going to choose acetylide. That's supposed to be a lone pair there. Sorry about that. Acetylide is the conjugate base of an alkyne which has a pKa of 25. So this is both a good nucleophile and a good base. So we would need to be thinking about the SN2 reaction and the E2 reaction. But for the primary alkyl halide, what do we remember? We remember that SN2 is fast because of minimal steric hindrance, whereas E2 is slow because of fewer number of beta protons and because the alkene that would form is not that substituted. So we would say that SN2 is fast, E2 is slow, so we would only worry about the SN2 product here. We would show that by having the nucleophile attack from the backside and the leaving group leave to give us the following product, where we've made a new carbon-carbon bond between the alpha carbon of our alkyl halide and the negatively charged carbon of our alkyne. All right, finally, let's consider let's consider a situation in which we use one of our molecules that's a good strong base, but a poor nucleophile due to steric hindrance. This is T-butoxide, which is a good strong base. Its conjugate acid has a pKa of 19. You wouldn't be expected to memorize that, but you could see it on a pKa table, or you could just remember that it's an alkoxide, so its pKa should be greater than or equal to 16. pKa, the conjugate acid, should be greater than or equal to 16. It's a bad nucleophile in terms of sterics. So now let's think about using the following alkyl halide as starting material. All right. So this is a secondary alkyl halide. We would say that SN2 is okay and E2 is okay. But because we're using a poor nucleophile that's sterically hindered, no SN2, we would expect to only see E2. Now, let's look at this molecule. As we've drawn it, let's look at the beta protons. Here's the alpha carbon, the one that's attached to the leaving group. Here's beta carbon 1. And here's a beta carbon 2 with alpha proton A. Notice that beta carbon 1 has no protons on it, so we don't need to worry about elimination from beta carbon 1. Beta carbon 2 has one and only one proton on it. That wedge there is a CH3 group. As it's drawn here, that proton is not anti to the leaving group. However, we can rotate around a carbon-carbon bond such that we move beta proton A down into the page to occupy the wedge position. And if we did that, then that beta proton A would be anti to the leaving group. So let me draw for you what I'm talking about. We're rotating around the carbon-carbon bond between alpha carbon and purple beta 2. And if we do that, the benzene ring, which used to be in the plane of the page, angled up towards the top of the page, is now going to be angled towards the bottom of the page and above the plane of the page. Beta proton A will be back into the page, and then the methyl group will be in the plane of the page. All right, now the leaving group iodide is anti to the beta proton, so that our base can so that it can line up with the carbon iodide sigma star, so that the LUMO can spread out onto the beta proton by hyperconjugation. Now that it's anti to the leaving group, we can do the elimination reaction. Notice that as we form the new pi bond between alpha carbon and purple beta carbon 2, that the two benzene rings are both on the same side of that newly forming pi bond. So in the product, the benzene rings have have to be on the same side. In other words, this is the only product that we can, the only elimination product that we can observe. We do not see, I'm going to use pH as an abbreviation for phenyl, which is a way to describe an adjective for the benzene ring. Phenyl group is another word to describe a benzene ring attached to something else. We do not see the product where the benzene rings are anti to each other. Now, as an exercise, it would be interesting for you to ask, what if I wanted to get that product where the phenyl groups are trans to each other? What would the starting material have had to be? What would it had to have been? Whatever. See if you can figure that out, what the structure of the starting material would have to be in order to get you the E stereoisomer instead of the Z stereoisomer. This is an example, it turns out that the E2 reaction is an example of a stereospecific reaction, meaning if you start with this specific stereoisomer, you have to get this particular stereoisomer as your product. And we'll see that a different stereoisomer would lead to this E stereoisomer. Okay, there are a lot of problems like this on your practice exam. In particular, there are a lot of problems, there should be quite a few problems that deal with this issue. Remember, in order to be reactive, a beta proton must be anti to the leaving group, and you'll need to consider whether it's possible for you to rotate around carbon-carbon bonds between alpha and beta carbons such that a proton can be anti to the leaving group. Okay, so in the time that we have left today, so far we've considered the concerted versions of these reactions where you have a good nucleophile or a good base that don't want to wait around and instead do the attacking of the alpha carbon or the beta proton to give you substitution or elimination products. However, what if we have a situation like this? What if we have a tertiary alkyl halide and something that is a good nucleophile but not a good base? So let's go ahead and use perhaps this thiolate that's a good nucleophile but a weak base. The thiol has a conjugate acid. The thiolate has a conjugate acid thiol whose pKa is around 8. All right. Well, we would say that SN2 is okay for this nucleophile, but there should be no E2. However, our alkyl halide is tertiary, so there can be no SN2, whereas E2 is okay. So we've ruled out SN2 for the alkyl halide. We've ruled out E2 for the nucleophile. So what can happen? Well, nothing, at least not until something changes in the structure of the alkyl halide. And this is going to take us back to one of the mechanistic hypotheses we discussed early on. This was one of the stepwise mechanistic hypotheses. So first, realize that bonds in organic molecules have vibrational frequencies. You can think of them as springs. So the You can think of a spring bonding the Cl to the carbon, and you can think of this sort of going back and forth with some vibrational frequency. An example of that I can show you in my colleague Dan S's Organic Reactions Animations app, which you can get. It's called IORA, which you can get from the Apple App Store for free. It's also available as a website for Android devices. And I'm going to show you the structure of tert-butyl iodide. This is a tertiary alkyl halide. The leaving group is iodide. And I'm just going to press play, and this is going to show us some of the vibrational frequencies of this molecule. All right, do you see how the bond between carbon and iodide is changing there? Do you see how it's fluctuating a little bit? At some point, if the molecule has enough internal energy, the spring can sort of snap and iodide can leave. Now, sometimes people have a hard time with that conceptually. What makes the iodide just leave? And the answer is, if we plot energy, potential energy versus distance between carbon and iodide, we would see at infinite distance, here is energy 0. At infinite distance, they don't interact with each other. Sorry, I needed a little bit of a thinner line there. When they're infinitely far apart, they don't interact with each other. The blue line will represent their energy as they get closer together. As they get closer together, there is bonding that occurs between them. There's an energy minimum that occurs at the equilibrium distance in that bond between carbon and iodide. And then as you start to get past that equilibrium distance, energy increases again, and you start to get repulsion between the two nuclei. Okay? So again, as we separate carbon and iodide infinitely, there's no interaction. As we bring them closer together, there's a covalent bond that forms between the two of them. There's an energy minimum, and then you get to an energy maximum as you start to approach even closer because of electron-electron repulsion. And the actual distance between carbon and, I guess we'll change this to iodide, the actual distance between carbon and iodide changes based on the amount of kinetic energy a molecule has. You can think about a given molecule sort of rolling around the bottom of this energy well. And as it does so, the distance between carbon and iodide changes a little bit, and you get oscillation here. If you supply the molecule with enough kinetic energy, either by increasing the temperature of a solution or, well, I guess that's the only, if you increase the kinetic energy of a molecule, which it can get just by randomly bumping into other molecules in the solution, if you provide the molecule with enough kinetic energy, you may eventually get to the point where you get enough to get out of this well completely and get to infinite distance. And this is what we mean when we show an arrow here and the leaving group leaving. We just mean that at some point the molecule has enough internal energy to break the carbon iodide bond and to let the iodide go free. You can think of it as the spring snaps. And iodide says, "Wee, I'm free." And it's gone. Okay? Now you might expect that to be slow because it's uphill in energy. Once that leaving group leaves, you have a carbocation and the leaving group. The carbocation's high in energy because you've lost a carbon iodide bond. You've broken a bond, and so that's quite uphill in energy. So you'd expect this to be slow. Nevertheless, if there's nothing else that can happen, nothing else going on, that can eventually happen. So if I had this alkyl halide as my starting material, I guess we've chosen iodide, so I'll make that change here. If I can't do SN2 because I'm in a tertiary alkyl halide, and if I can't do E2 because I don't have a strong base, then what am I left with? Well, all I'm left with is I can have the leaving group leave to give me a carbocationic intermediate, and then I need to ask what happens now? How will this molecule react with the carbon with the carbocation? And to answer that question, we'll wait till next time. You can imagine that the nucleophile / base could attack the positively charged carbon. You should think about what the LUMO is. But then I want you to think about, really, what is that LUMO? You would say it's the empty p orbital on that carbon. I want you to think about whether or not that LUMO can spread out, and if so, to where. That concept is going to be key to predicting what happens next. And with that, we'll end for today. Please stay warm and stay safe, and I will see you on Friday.